Hello again. Here I'm going to do problem 34 from 3.3. In the previous problems, we've just been given information about the derivative, the second derivative, and we had to deduce what the graph must look like, or what the intervals of increase and decrease are, or concave up and concave down. Now we're given the equation, the function, the formula for the function. Yes, now we could just put it into a calculator and look at the graph. But I want you to know how to do this algebraically on a few simple graphs. Nothing real complicated. So let's look at number 34. So there is a systematic way to approach this. The questions are: find the intervals of increase or decrease, find the local max and min, find the intervals of concavity, the inflection points. Okay, so of course we're going to need the first derivative and the second derivative. So let's just get them. The first derivative is going to be 36 plus 6x minus 6x squared, right? The second derivative, let's just get it, is going to be 6 minus 12x, right? Okay, this doesn't look too bad. So I took the derivative of this, 6 minus 12x. I took the derivative of this, 36. 2 times 3 is 6. 3 times 2 is 6. And there we go. Okay, so to find the intervals on which the function is increasing or decreasing, you find out where f prime of x is equal to 0. Okay, so you set this to 0 and solve for x. So we've got 36 plus 6x minus 6x squared equals 0. Okay, we can divide both sides by 6 and simplify things a little bit, right? Okay, so now we've got to figure out, okay, what can we do with this? We could multiply both sides by -1. Maybe that's a little better. Well, most people don't like dealing with a negative in front of the x squared, so let's do it that way. Okay, now I'm going to go back up here and factor this. What if you can't factor this? Well, then you have to use the quadratic formula. Okay, so let's assume we can factor this. Let's say x minus 3 times plus 2. Okay, I'm going to check it. -3 times 2 is -6. Negative 3x plus 2x gives us the middle term, which would be negative x, so that works, and then x squared. So this works. So we've got two places. X equals 3, x equals -2. So these are the two places where the derivative is 0. Okay, so we can make a little chart. The two places where the derivative is 0 are the only two places where you could change from increasing to decreasing or decreasing to increasing. Those are the only two places. So we've actually got two different things we could do here. We could look at what the second derivative is at -2 and what the second derivative is at 3. So we could put 3 in here. 6 minus, this would be 36, right, would be a -30. If we put in a 3, 3 times 12 is 36, so it'd be a -30. If we put in a -2, we would have 24 plus 6, which would be, okay. But that doesn't matter. What matters is the second derivative at -2 is positive. The second derivative at 3 is negative. So this means that at -2 the function's concave up. So that's where we have a local minimum. At 3, the function is concave down, so that means we must have a local max. So local min, local max. So now they say find the local maximum and minimum values. Okay, so we determined that at -2, the function's concave up, so that's got to be a minimum. So our value that we're after is the function value at -2. So you would put a -2 into this function and get out a y. That would be your minimum value. Your local maximum is at 3. So that means if I put 3 into the original function and I get out a number, that's the y coordinate of my maximum. That is the maximum value of the function there. That's the local, and the f at -2 would be the local minimum value of the function. So let's see, let me get those. I'm going to put them into my calculator. So what I'm going to do is put this into, put this function in there, 36x plus 3x squared minus 2x to the cubed, and just put in those values. So at -2 I get -44. At 3 I get 81. So the local maximum occurs at x equal to 3, and it's 81. The local minimum occurs at x equal to -2, and it's -44. Okay, now we also could have done this. Let me show you this. We also could have made a table. So the only two places on the whole graph where the function can change, increasing to decreasing, decreasing to increasing, is at -2 and 3. So we can make a chart. What goes on from 0 to -2, -2 to 3, and 3 to infinity. I'm sorry, not 0. This is defined for all real numbers. So I can make a little chart. So I can say, okay, if x is less than -2, like -5, this product is going to be negative, so the function's decreasing, right? From -2 to 3, from -2 to 3, like at 0, we would have -3 times 2, which would be negative, so the function's decreasing. Okay, wait a minute. I made a mistake here. If I put in, say, a -5, this would be negative and this would be negative, so my function, my derivative would be positive, which would mean that the original function is increasing. I'm just picking any value from between -infinity and -2. Imagine putting it in there. Imagine I don't need to know the value, I just need to know the SIGN. So here I put in 0 and I would have -3 times 2, that's a negative. If I put in, say, -5, I would have -8 times -3, which would be a positive. And then if I put in anything bigger than 3, I'm going to have a positive. So the function's increasing. So I got 2 bits of information. Here's the interval where the function's increasing, here's where it's decreasing, here's where it's increasing. From the second derivative, from the value of the second derivative, at these 2 x values, I can tell whether it's a local max or local min. But I can also tell from this. If I go from increasing to decreasing to decreasing, then that's got to be a local max. So I'm saying at x equal to negative 2, I have a local max. Here, at 3, I have a local min at x equal to 3. Because I go from decreasing to increasing. So that's got to be a minimum. Okay. Now we've got intervals of concavity. Okay. So intervals of concavity. The only place that you can change concavity is where the second derivative is 0. So I'm going to set the second derivative to 0 and solve for x. Whoops, excuse me. So we would have 6 equals 12x, or x equals 6 over 12, which is 1/2. Okay, so at 1/2, it looks like we could have a change in concavity. We don't know for sure, we got to test it. So that's, at 1/2 is the only place we could change. So we make a table again. We go from negative infinity to 1/2 and 1/2 to infinity. Because everything below 1/2 must be one way, everything above 1/2 must be another way. That's the only place it could change. So if we're bigger than 1/2, let's say, let's start here. Smaller than 1/2, let's say 0. Well then, if x is 0, the second derivative would be 6, it'd be positive. So that means the function is concave up on that interval. Okay, what about bigger than 1/2, like 4? Well, 4 times 12 is 48. 6 minus 48 is going to be negative. So it's going to be concave down there. So we change from concave up to concave down. So there is an inflection point at x equal to 1/2. What is that? Well, we'd have to put in we'd have to put that into the function and find the y coordinate. So I'm going to do that now. I already have my function in there. So it looks like it's 18.5. So our inflection point is 1/2 18.5. Okay, so you know the inflection points, you know the local maximum minima points. Since we have the formula for the function, we can get the y values. You could sketch the graph even without a calculator. So what I want to see is not so much a sketch of the graph, because you can get it out of your calculator or Desmos, but this kind of work. How do you reason without the calculator? So it's kind of convenient. You have the answer. You just have to show the work to reason to the answer. See you again soon. Oh, I should mention that the additional homework for the weekend from this section, chapter 3.3, will be uh, 21, 23. This is from section 3.3, 25, 26, 32, 33, 39, 41. So this is section 3.3. And what we're going to do next is go to section 3.7, apply the same information, but this time we're going to have word problems. And then we'll be finished with purely derivatives. We'll go on to integration next week. See you soon.